humans may have already contacted alien civilizations. This was recently mentioned by a U.S. congressman. According to him, alien technology far surpasses humanity's current understanding. The reason for not disclosing it is to avoid panic. Setting aside the truth of this matter, what's truly worth noting is, if alien civilizations exist or have visited, what would they actually be like? You think this is impossible to guess. Wrong, because how life grows and civilizations develop is not entirely random. Nature has a very strict underlying rule. Form follows function. Simply put, life never just grows haphazardly. What kind of environment will more easily foster what kind of life? Gravity, temperature, light, radiation, resource competition will all gradually determine what a species eventually becomes, so aliens may not be exactly like us. But they also won't be completely incomprehensible. Quite the opposite. If they also need to survive and perceive the world and compete for resources and develop tools, then they likely will have some structures very similar to ours. Like eyes, like grasping organs, like brains for processing information. This isn't mysterious, because you yourself are a result of form-following function. Why do you have hands? Why do your hands have opposable thumbs and fingers and a thumb? Because you need to hold things and operate tools and perform fine motor tasks. Why do you have legs? Because you need to move. Why do you have a digestive system? Because you need to convert external matter into your own energy. Why do you have a brain? Because you need to judge, remember, calculate, and solve problems, including your heart, bones, and muscles. Almost every part of your body didn't just grow randomly. They are the result of environmental survival and competition. What is useful is more likely to remain. What is useless is more likely to be eliminated. Darwin noticed on the Galapagos Islands that different finches had different beaks. Some were thick and strong, suitable for cracking hard seeds and nuts. Others were thinner and sharper, suited for probing crevices for insects. They were all birds, but ended up with different tools, not because they wanted to be that way, but because the survival challenges they faced were different. The environment posed questions, and life had to provide answers. And nature didn't just write some answers once. A prime example is the eye. As long as there is stable light in a world, whoever learns to see first will more easily find food, avoid danger, and survive in the environment. So eyes are not something that only evolved once on Earth. Scientists believe eyes evolved independently many times. This means that life from different ancestors and different evolutionary paths converge on the ability to see. This is called convergent evolution, and eyes are just one example. Birds and bats are not closely related, but both evolved wings. Bats and dolphins live in very different environments, but both developed echolocation. Even photosynthesis didn't evolve only once. Koalas even have fingerprints, very similar to humans. The reason is not complicated, because some selective pressures are inherently universal. When problems are similar, the solutions can be similar. This is important because it means that while alien life may not look like us, they also won't be so bizarre as to be completely incomprehensible. If an alien civilization also needs to perceive the world, they might develop similar senses. If they need to move, they might develop limbs, competing for resources, manufacturing tools, processing complex information. Then they likely would also have some structures similar to ours, not necessarily 5 fingers, but most likely some kind of organ for grasping or manipulation. Not necessarily a human face, but most likely some kind of highly efficient sensory system for receiving external information. Not necessarily a human brain, but most likely a processing center responsible for integration and analysis. So those humanoid aliens in sci-fi are often criticized for laziness. But from a biological perspective, it might not be entirely far-fetched. If certain survival problems are universal in the cosmos, then life on different planets might indeed evolve towards similar directions. Of course, similarity doesn't mean they'd be identical. Life forms would change with their environment. In a low-gravity world, life might be taller and lighter because supporting the body and transporting nutrients would require less effort. But in a high-gravity world, life might be shorter, sturdier, and more compact, with denser bones and tighter structures, or they might evolve to live in water. Because in water, the burden of gravity is much smaller, If a planet is farther from its star and receives less light, life there might develop larger eyes or rely on other senses, like echolocation, heat sensing, or senses we haven't even imagined. If a planet has a highly elliptical orbit, experiencing extreme temperature fluctuations, life there might be better at hibernation, more resilient to extreme conditions, even developing near-dormant survival capabilities. Temperature also shapes body size. Larger bodies conserve heat better in cold, while smaller bodies dissipate heat more easily in heat. If a world has a weak magnetic field and high radiation, life there might have shorter lifespans and faster evolution, with quicker reproduction and selection, to cope with harsh environments. So in the end, we can speculate about alien life, but not arbitrarily. This principle affects more than just bodies. It can influence civilization itself, how it develops. Even among humans, civilizations from different environments might take very different technological paths. Some lands are easier to farm, allowing society to free up people who don't need to focus solely on survival, leading to more inventors, researchers, and knowledge accumulation. Some areas have abundant fuel, making industrial revolutions more likely. Some regions, with easier access to silicon, metals, and rare elements, might see faster technological development. Resource conditions directly influence a civilization's direction. Therefore, a truly intelligent alien species would not have developed its civilization from scratch. It likely emerged through competition, grew within resource constraints, and found its own way to survive under environmental limits. Once they reach this stage, they would likely seek more space, more energy, and more resources. This idea later led to a classic scale, the Kardashev Scale, proposed by Soviet astrophysicist Nikolai Kardashev in 1964. It classifies civilizations by their energy control capabilities. Type I civilizations can fully utilize all the energy of their planet. Strictly speaking, humanity hasn't reached this level. Type II civilizations can harness the energy of their entire star. For example, the familiar Dyson sphere is essentially such an idea. Type II civilizations can command the energy of an entire galaxy. Some people have extended this concept further. Type IV civilizations can utilize the energy of the entire universe. Type V civilizations can even traverse multiple universes. The concepts beyond that are essentially godlike. If such advanced civilizations exist, the gap between them and us might be beyond mere description of advancement. This leads to an uncomfortable conclusion. If there truly are civilizations far more advanced than us in the universe, how do they perceive us? If there are truly civilizations far more advanced than us, how do they perceive us? Perhaps like how we view bacteria. Looking at insects doesn't necessarily mean hostility, but they might not take us seriously either. However, the development of alien civilizations isn't necessarily linear. We always like to imagine advanced civilizations as constantly expanding, constantly conquering, and constantly consuming resources, but that's not necessarily the only answer. Not all civilizations will always expand outwards. There might be a type of civilization that, after reaching high technological levels, starts focusing its main efforts internally. It no longer expands its physical territory wildly, but shifts towards information, consciousness, and virtual space, moving more and more activities into a highly complex inner world. For such civilizations, progress might not be measured by how many planets they occupy, but rather by how much they know, how much they understand, and how much information they process. In other words, the advancement of a civilization isn't necessarily defined by territorial gains, but could be defined by the depth of their cognition. Ultimately, we still don't know if alien life truly exists, nor what they look like, or what path they might take. But at least there's one thing we're not completely in the dark about, which is that if life exists, it cannot completely escape natural laws. It will be shaped by its environment, limited by resources, forced to evolve by competition, and compelled to find solutions to problems. So if one day in the future we do encounter an alien civilization, they will likely have some characteristics that we can immediately recognize, because in a sense, all intelligent life is answering similar questions. But this is just the first layer of deduction. The bigger question is, how rare is intelligent life? Because from an ordinary planet to a civilization capable of looking at the stars and contemplating the universe, there are too many hurdles to overcome. Yet it's not entirely impossible, because it has already happened once. You and I are proof of that. The question is, how rare is this phenomenon in the universe? Did it only happen this one time? Or are there other civilizations in some corner of the galaxy, also looking up at the sky? To answer this question, we first need to broaden the definition of life. Because we can't assume all life in the universe must be like Earth's. Earth life depends on water, but this doesn't mean life elsewhere must also depend on water. They might rely on other solvents, other chemical systems, or even other energy exchange methods, as long as a system acquires resources, grows, and replicates itself. It's already close to the life we're discussing. But from self-replicating life to a civilization that can communicate with us, there are many more steps. It must first appear on a suitable planet. It needs a stable energy source. It must continuously evolve through competition. It needs to develop stronger perception, stronger judgment, and better problem-solving skills. It also needs to survive long enough not to be wiped out by an asteroid, global freezing, supervolcanoes, or self-destruction before its technology matures. Finally, it must develop technology and be willing to send out signals, and these signals must last long enough for us to receive them. This is what the Drake equation tries to do. It doesn't directly answer where aliens are. It breaks down the problem into how many civilizations in the universe can be detected by us. It breaks it down into a series of smaller questions and then estimates the probabilities for each step. It asks, how many stars each year are born suitable for life? Of these stars, how many have planets? Of these planets, how many have suitable environments? Of the suitable environments, how many actually develop life? Of the life-bearing planets, how many evolve intelligence? Of intelligent life, how many develop technology and start sending out signals? Finally, how long does such a civilization typically survive? If you multiply all these factors, theoretically, you can get a number. At this moment in the Milky Way, how many civilizations are there actively transmitting signals in some way? Let's look at the first few parameters. This part is relatively well observed astronomically. In the Milky Way, every year about how many stars suitable for life are born? Let's take an average of 5 here. Next is the proportion of stars with planets. This number isn't low. Let's estimate it at 0.9. Next, for each star system, the number of truly habitable planets. Using a more conservative estimate, it's about 0.003. This is still okay. The real trouble is the signs of life later, because we have almost no samples for these. Like the probability of life appearing, we only know life appeared on Earth. And soon after Earth cooled, life seemed to emerge. This makes one think life isn't that hard to find. But there's also a glaring fact. As far as we know, all life on Earth seems to trace back to a common ancestor. This means, on this planet, crossing the threshold from inorganic to life, we've only seen one successful case so far. So is this event very easy to happen? Or extremely rare? We can't really say right now. If we use a more pessimistic estimate, let's just push this probability very low, directly to 1 in a million. Next is the probability of intelligence emerging. This is also difficult. Life on Earth solves puzzles and uses tools. Even animals showing some cognitive ability are not uncommon, like octopuses. Some birds are quite smart. But if your standard is not just smart, but smart enough to build a technological civilization to send signals to the universe, then Earth currently has only one sample, which is humanity. So, if we continue down this pessimistic path, let's give another 1 in a million. Then comes the probability of technological communication. This one is actually rated higher, because once a civilization develops to a certain extent, it doesn't necessarily have to deliberately signal. It will expose itself unknowingly. Industrial activities alter atmospheric composition. Radio waves leak out. Satellites orbit. Even humans actively send messages out, like the Arecibo message in 1974. So let's set this at 0.7. The last parameter is the most critical. How long a civilization survives. We have no way of verifying this now, because humanity hasn't reached its end. We don't know if a technological civilization will end prematurely in nuclear war, or survive disasters and spread to other planets, living for millions of years, hundreds of millions, or even longer. But this parameter has a huge impact, because the longer a civilization lives, the higher the chance of being detected. A civilization lasting 100 years and one lasting 1 million years are completely different concepts, and this is what makes the Drake equation so interesting. It makes you see whether the universe is empty or full. Often, it's not determined by the large numbers at the beginning, but by a few later probabilities you can't be sure of, which lead to two completely different conclusions. If we calculate pessimistically first, life is hard to arise, and intelligence is hard to arise. In this scenario, even if civilization lifespan is incredibly long, the final result is still close to zero. Meaning, in the Milky Way, there might be no civilizations currently detectable by us. The universe isn't empty, but we are too sparse, too scattered, and out of sync. But if you slightly change the first two probabilities, the conclusion flips instantly. If life's emergence is almost inevitable, and intelligence is just a matter of time, then the result is no longer zero. Even if a civilization lasts only 1,000 years on average, there could be 9 communicable civilizations simultaneously. In the Milky Way, if a civilization crosses a certain threshold, it could achieve functional immortality, lasting for a very, very long time. Then this number could jump to 9,450. This is the most fascinating part of the Drake equation. It doesn't truly answer for us whether there are others in the universe, but it breaks down the question from a mere thought into a series of discussable, debatable, and quantifiable numbers. The final result gives is not a definitive answer, but a framework for thinking about the possibility of extraterrestrial life. But these are two completely different universes. In the first universe, the galaxy is terrifyingly quiet. Intelligent life is so scarce they barely meet. We might be the only ones nearby who can speak out. If that's the case, humans should learn not to kill themselves first. Because in this vast darkness, we might be the only ones who can see each other. And in the second universe, civilizations are not uncommon, but they are widely spread and short-lived, or their communication methods don't match ours at all. But if they are really numerous, then where are they all? This is the Fermi Paradox. It doesn't say there are no aliens in the universe, but if they are really numerous, then we should have seen some signs by now. One explanation is chilling. Perhaps civilizations in the universe don't stay silent, but are afraid to speak. Because if a civilization exposes its location, it's like putting a target on its own head. And for truly advanced civilizations, launching an attack might not require a fleet, might not require landing, might not even require face-to-face contact. Just accelerate a large enough object to extremely high speeds and throw it. Life on a planet could be directly wiped out. Under these circumstances, the safest strategy is not communication, but silence. Whoever exposes themselves first is the first to be in danger. This is the answer many are familiar with. The dark forest. But the dark forest isn't the only answer. There's another, more desperate possibility. They aren't afraid of us, but simply don't care about us. Once the technological gap is large enough, communication itself becomes meaningless. Just like history and future. Not because you hate them, but because the gap is too large. They don't understand you, and you don't need to explain yourself to them. If they might have noticed us long ago, but simply aren't interested in responding. We think we're looking for neighbors, but in their eyes, we might just be a primitive species that just learned to make fire. Of course, there's a third possibility. As civilizations develop to a high enough level, they don't necessarily become more hostile. They might become more cooperative. Because the stronger the technology, the higher the cost of mutual destruction, the more powerful a civilization becomes, the more likely it is to understand that long-term survival is more important than short-term plunder. Just like human society's development hasn't always been about splitting into smaller tribes, but has been expanding cooperation. From tribes to city-states, to nations and alliances. Following this path, an advanced civilization might also view new intelligent species as potential future members, rather than immediate threats to be eliminated. So the most unsettling part of the Fermi Paradox isn't whether it has an answer, but that these three answers, none of them are easy. Either the universe is full of silent hunters, or there are civilizations in the universe that have seen us, but are too lazy to respond. Or they are waiting for us to grow to a level worthy of a response. Until then, the entire universe will appear quiet. But there's an even more fundamental question. Even if there are many worlds suitable for life, how did life itself begin? To this day, there is no definitive answer. But in general, scientists aren't completely clueless. Because all life on Earth relies on a few basic building blocks. such as fatty acids, amino acids, and nucleotides. These substances may have existed not only on early Earth, but have also been found on some asteroids. This means the raw materials for life may not be scarce. The first step is the appearance of a boundary, because for a set of chemical reactions to become true life, it can't remain a homogeneous soup forever. It needs to separate itself from the outside, and fatty acids happen to do this. These molecules have a hydrophilic head and a hydrophobic tail. This allows them to form membranes. After being put in water, they line up by themselves, finally forming a single membrane, forming structures like small bubbles. This is the most primitive room. Without walls, there are no cells, no boundaries, no truly independent life units. More importantly, these cell-like structures can even spontaneously divide. They can also enclose molecules, improving local reaction efficiency. But boundaries alone are not enough. Life still needs function. At this point, amino acids and nucleotides become important. Amino acids later became the basis of proteins. Nucleotides participated in RNA and DNA information systems, especially RNA. It's crucial because it's not just a carrier of information. Short-chain RNA can also catalyze chemical reactions. This means, before life truly appeared, there might have already existed on Earth molecules that could both participate in reactions and begin to carry information. Moving one step further, you will find what life needed earliest, perhaps not the complete, sophisticated cells of today. It needed only a few conditions to appear simultaneously. Boundaries and energy. Molecules carrying information. Plus a crucial element, selection. Because without selection, more molecules would just be a random collision. Complexity wouldn't increase on its own, only when certain combinations are more stable. Easier to replicate. Easier to continue existing. Did selection begin to emerge? And once selection existed, chemistry was no longer just chemistry. It would start to move towards life. There's another important point here. The origin of life might not have started with complete cells. Then metabolism. Some chemical reaction networks would preferentially generate molecules that help themselves continue. This is called autocatalysis. If such a network can sustain itself and expand itself, it would already resemble the earliest metabolism. In other words, before organelles and complex genetic systems took shape, Earth might have already seen some kind of self-propelling chemical system, and early Earth happened to provide a very good environment for this. The Earth at that time was like a giant chemical battery. The ocean was acidic and electron deficient. The underground was alkaline and electron-rich. This strong imbalance provided continuous energy for early chemical reactions. Deep-sea hydrothermal vents, volcanic hot springs, evaporation pools, underground caves. These places, extreme and dangerous today, might have been the stage for life's earliest emergence. What's more interesting is, life might have appeared earlier than we think. Earth formed about 4.54 billion years ago. Liquid oceans appeared around 4.4 billion years ago. And the earliest life may have appeared around 4.3 billion years ago. This means, from Earth cooling to supporting life, to life actually appearing, the time gap might not have been long. This at least indicates one thing. The emergence of life might not be as unattainable as we once thought. Life isn't a pure magic trick of luck. It's more like when raw materials, energy, boundaries, information, and selection come together. Matter is pushed step by step in a specific environment. In other words, life didn't appear suddenly. It's more like early Earth's environment gradually pushed a pile of molecules into life. If life isn't magic, but a result that can be pushed step by step in the right environment, then the next question is straightforward. How many such places are there in the universe? The answer is yes. And not just a few dozen, but so many they exceed our wildest imagination. According to NASA's latest statistics, humans have confirmed over 6,000 exoplanets. Kepler and its later K2 mission alone found over 2,600. The one thing confirmed discoveries truly changed wasn't just making us aware of more distant planets. It completely shifted the focus of the entire question. We used to worry about whether there might be no other worlds in the universe. The question has changed to how many worlds like ours exist, and how many of them have developed life, and how many have developed intelligence, and how many have developed civilization, and how many have developed advanced civilization, and how many have developed interstellar civilization. Now we face another question. Among so many worlds, is there really one that grew life? Because, if other stars commonly have planets around them, Then the next question is no longer about having targets, but which targets are worth focusing on? Which planets are Earth-sized? Which have suitable orbits? Which might retain an atmosphere? Which are worth further investigation? What gases are in their skies? In other words, Kepler's most important meaning isn't finding aliens for us, but truly expanding our search scope. To put it more directly, Kepler made humanity realize for the first time we are not in a universe with almost no planets, accidentally stumbling upon a miracle. We are in a galaxy filled with planets everywhere, slowly sifting, slowly screening, slowly approaching that crucial question: is life unique to Earth? Of course, many targets don't mean the answer is found. To this day, we still haven't obtained confirmed evidence of alien life. But compared to decades ago, the situation is completely different because the most important thing now is no longer guessing if other worlds exist, but whether these worlds once had life. I'm Lao Mai. See you in the next universe.